I think it's about time to start, so I'm just going to plow ahead. I think some more people may turn up as we're going, but we'll see. So thank you all for coming. I'm impressed you've lured yourself away from Stampex. There's a lot of you here, so they're not doing a good job. So this talk is going to be about fraud detection, but fraud detection is a ginormous, gigantic field. So it's more of a kind of taster of the kind of things that you can do to detect fraud. And I hope it'll give you some ideas and it'll let you talk to people about fraud problems and talk about the kind of techniques that are used to detect these kind of situations. Now, one thing there is joined in. This is only the second time I've given this talk, so I really appreciate any feedback. It's kind of a technical talk, so it's not always easy to know how well that's going to go across with people, what makes sense, what doesn't make sense, what needs more explanation, what needs less. So please let me know. That would be really appreciated. And secondly, there is a bunch of code in here, which is all on a GitHub. So don't worry too much about trying to follow along with any particular bit of code. If you do need to look at it later, it's all on there, including the data that goes with it. So fraud is a big problem. But when people introduce it, they tend to introduce it with big numbers, big scary numbers in the billions, and I prefer some small numbers. 5% is the average revenue businesses lose to fraud. 3% is the police budget here in the UK that is dedicated to fighting fraud. 0.1% is the percentage of transactions a large retailer can expect to be fraudulent if they've implemented a decent level of checks, if they've got verified by Visa, if they're doing AVS, those kind of things. But 8% is the percentage of transactions that get flagged as fraud. And I'm sure anyone that's had a call from the fraud detection robot on their credit card saying they need to confirm some transactions with you know what that's like. It happens a lot more than your credit card actually gets used for fraudulent activity. So how do we do something about this? How do we face these kind of numbers when fraud is so relatively rare but so easy to detect erroneously? Because there's a lot of cost to it, not just the monetary cost, not just that 5%, there's the cost of reputations, and there's cost to actually make things better, to go out and fix the problems that the fraud has caused. Well, there's kind of 4 general areas of techniques that seem to be the main ways that fraud is dealt with. And we're going to look at really these 2, anomaly detection and supervised classifiers, and we're going to touch on rule-based detection. The 4th quadrant here is a very interesting one, complex event processing. This is kind of the emerging way of doing things. It's almost a combination of the 3. It's doing rule detection and processing data and looking for anomalies in a very fluid and dynamic way with very large amounts of data. So if you're at Visa, this is the kind of work you'll be doing. But some people will argue there hasn't been a true CEP system developed yet. So I'm not going to talk about it in here. I'm happy to talk about it a bit afterwards, but it's not something that is in the everyday world of sort of smaller products that we're looking at the moment. So we looked at the fact that fraud was rare earlier, and I wanted to just point out quite how rare it is. Let's say that we can make a classifier or a detector or a fraud tool that would give you a 99% accuracy. So if you gave it 1,000 transactions, it would give you 99% accuracy across that. That sounds pretty good. That sounds like something that would really help us in our business. But if we did that, we would find that almost 990 of them that were legitimate, we marked as legitimate. That's great stuff. We've gone away and detected that that isn't fraud. We've not done anything about it. We wouldn't miss any fraud. But we would detect 10 transactions which were legitimate as fraud. And we would pick up the 1 out of the 1,000 that was fraudulent, which means we're 90% wrong. We've got a huge error here, and this is why we have that 8% difference. This is why we have the fraud robot phoning up. This is why it's expensive, because every time you get a fraud incident, you have to go and investigate it. You have to go and do something. Someone somewhere is having to take action based on this. So it's tricky to deal with such rare systems. So how can we detect it? What can we use to make detecting fraud easier? We have to know something about the problem. And the important problem you can always go back to with fraud is that fraud is about money. People are trying to make money with these scams. Think of mobile phones. There's maybe two kinds of easy fraud you can do with a mobile phone. One direct, one intermediate. So a direct kind of fraud might be that you clone a phone. This used to be a problem with when you had analog versions of phone networks, and people would take over someone else's identity, and they would make calls on it. And they will go away, and they will have those calls on the cloned phone billed to the original subscriber, which is great because the person who's cloned the phone can sell that phone to someone that wants it for a certain amount of money, so they get paid. And the person that buys the cloned phone can then use it and hammer as many calls through it as they can up until the point it gets shut off. But there's other things you can do with a phone. You can take a phone, a pay-as-you-go phone, a legitimate phone, and top it up with a stolen credit card. You put 50 quid onto that phone, and then you immediately call a overseas premium rate number. And that premium rate number is owned by some counterparty of yours, someone that you're working with. The money goes to them for your calling, and they have it legitimately. They can say, look, we just got called up. Of course we got paid for this. And because they're over jurisdictional bounds, it's hard to prosecute them. It's hard to go after them. So that's a kind of way of going an intermediate level. But in both those cases, something is different about that kind of usage. And that brings us to kind of the first idea, which is anomaly detection. If most people on your mobile phone network top up on a pay-as-you-go scheme, they top up around 20, 30, 40 pounds each payday, then you kind of have a pattern about it. If someone starts topping up 50 quid 10 times a day, that is unusual, that is suspicious, and perhaps we can detect that. For a cloned phone, if you are calling mostly your friends who live in the same city as you, and you sometimes call your parents who live, a couple of 100 miles away, and you maybe order a pizza, but then suddenly you're making 20 calls a day to Pakistan, then there's something suspicious that has happened. Some big change has happened in your behavior, and perhaps we can detect that. So what I thought we'd look at as an example is something maybe a little bit closer to home, which is click fraud. So when you have pay-per-click advertising, that is a source of income. That is a place someone can make money. And click fraud is when people are clicking on advertising without genuinely being interested in the product, without going there to find out more about it. And that is something that can be very difficult to detect. Now, some people have clicked on competitors' products to try and use up their marketing budget and so on, the network's pretty good at detecting that kind of low-level activity. But the bigger problem is you set up a site that has a lot of adverts on it and then push clicks through it using a clickbot, using maybe hacks. So perhaps you use clickjacking, an iframe overlay, or something that is diverting clicks from a legitimate but exploited website to go and click on your ads. Or it could be simply that you are paying someone, because if you make 10 cents a click, you can afford to pay someone 6 cents a click, and that can turn into a reasonable wage in some parts of the world. So that's tricky. It's tricky to detect. You can look at it and say, oh, it was a bot, so it all came from one IP, and it was all in a very short duration. But intelligent bots will go over hacked machines. They will be over a botnet where you have millions of different IPs and a whole range of different machines and configurations actually connecting to this. So it might be difficult there. And with human clickers, it could be even worse. There was a case in Japan, I think around 2006, 2007, the Kiyashinku, I'm sure someone can pronounce Japanese, credit card, where a few blogs in Japan had decided to complain about the fact that Japanese credit cards companies were really screwing over consumers, charging really high rates. And what they'd done is caused a protest where people would go and click on ads to use up the marketing budget. But it was such a widespread thing, it turned into a massive coordinated attack on the budgets and on the click adverts of credit card companies in Japan. That's almost indistinguishable from normal traffic. If you just look click by click, there's almost no way of saying that's different. So what we'll do is look at just one signal, and that signal will be number of clicks per day, or number of clicks per unit of time. Now, real networks will employ hundreds of signals. They will employ as many different parameters as they can, but the idea is pretty much the same. And the idea is that you want to find the point at which things change. So what we have here is some noisy data. There's some clicks that happen throughout a week, people clicking around. And at some point, some fraudulent traffic was added. And you can kind of see, plotted out like this, you can kind of see this bit's higher. There's some extra traffic in there. There's something that wasn't supposed to be there. But can we detect it? What we would like to do is find this point. But we have to think about two types of errors. What if we find a point beforehand? We say, hey, fraud is here. Well, that's a false alarm. We have to investigate it. We have to see, is anyone doing anything bad? Are there clicks we should be rejecting? So that has cost to it. That has literal time and money cost to it. But if we don't detect it by here, then we're going to find that we have people exploiting us and potentially making money. So we're paying out here as well. There's cost if we don't get this point right. And those costs trade off. If it's very cheap to detect, investigate a fraud, maybe you prefer to get a few false alarms. If it's very expensive to investigate, maybe you prefer to not pick up on a fraud right away. So what we need to do is to build some kind of detector. And most anomaly detection systems work in the same way, working with a buffer. They're working with a window. They build up a moving window through time of the past period. And they give that buffer to a detector, which makes a decision based on what it's seen in recent history and what the current signals are. The detector is pretty simple. All we do is, from our buffer, come up with an expected number of clicks, saying, based on what we've seen for the last n days, we expect today to have about this many. And then if that is combined with a sensitivity, a fixed value that we can give it that says, we are this concerned about it, we are that concerned about it, gives us a threshold. If it's greater than the threshold, we trigger an alarm. We say something's happening here, it needs investigating, whether or not that's correct. And we can build something like this very, very easily. So this is just some simple PHP. This fraud clicks file is in the GitHub. And all we're doing is going to loop over it and build up a window of 7 days. And out of that, we're going to calculate two things. We're going to calculate the average, which is there. And we're going to calculate the standard deviation. And for people that maybe have blocked out some maths classes from many years ago, the standard deviation and the average are part of something called the normal distribution, the bell curve. And those are two important parameters. The average tells us where the middle is. But the deviation, or the variance, tells us how wide the curves are. So we can see that if we have had, over the last week, a very tight curve like this, then higher values, they're rare. We don't expect them. But if we've had a curve more like this brown one, the higher values are much more likely. We can see here 17 is like 2-3 times more likely on the brown curve than it is on the blue. So it allows us to measure our expectation, measure how confident we are. So all we do is take our average, add a configurable number of standard deviations, that's our sensitivity parameter, that's just an argument we're going to pass in. And if the current day's clicks are higher than that, we'll signal alarm. We'll say something needs to be looked at here. So we can put that in, and we'll get a little graph like this. We can see that our expected value tracks just above our data, and then just 1 day after fraud's added, it detects it, and it says something's happened here. But in the time beforehand, there are actually 18 points where it detects it. It detects that the threshold has been breached by pure chance, just by the random noise of the data. No fraud had been added at this point, yet we've detected it. So that's costing us a lot of time. So maybe we'll think, we'll increase the sensitivity. Great. 2.7 sensitivity, well, we're tracking way above. We only get 1 false alarm. But then it takes us 18 days before we can actually detect the fraud. So we have to decide which way our trade-off is. And obviously, this is on data where we know exactly which day it is. We can say how well we're doing. In real life, you don't know this. You can't determine which side of this you're on until you actually start getting results and investigating them. So how can we improve on this? Is there a way to automatically detect the sensitivity? And it turns out that there is. And this is where those other signals come into play. You can use other information to make your detection better. So what we're going to use is a little bit of information that is built in to the data we already have, which is which day of week it is. Because we might reasonably think that you get different traffic online to the kind of sites you advertise on different days of the week. And you might reasonably think that that would have an effect. So if Friday is a day everyone's messing about at work and not doing anything, there maybe is just more traffic around, people will click on more ads, so you shouldn't be surprised if you see a higher number that day. But if you see a high number on Sunday where no one's online, that's a concern. So what we'll use is an algorithm called sickness availability. But the general idea behind this is the way that you will bring in as many signals as you want. Now, this comes from the world of biosurveillance, which sounds cool, but it's really about detecting outbreaks, detecting disease. So let's say that you are tracking how many people have the flu, and you want to see, is there about to be a big ramp up in the number of people that have the flu? Is there an epidemic? Because we need to get stocks of vaccine and various other things set up. Well, if there is, then we need to consider two factors. We need to consider how sick are people at the moment, because a high number of people with the flu in the winter is way less unusual than a high number in the summer. So we need to consider the general level of sickness. And we also need to consider how many doctors there are, because you can only be diagnosed with the flu if there's someone there to diagnose it. And at weekends, less doctors are at work, so there is simply going to be a lower number. So what sickness availability does is calculate two values. The availability over the day of the week, so how much are people around on a Tuesday, how much are people around on a Wednesday, and the sickness, which is over, say, the last week. How sick have people been over that last period? And that allows us to calculate an expected score. Using that expected score, we work out a probability of getting the actual score we've seen using something called a Poisson distribution, which we'll come back to in a little bit. So this is the detectors, very much the same thing as we just saw. We're going through the fraud clicks, but this time we're building up two windows. We're building up two averages. We're calculating the average for the day of the week. So we're going to go through and work out what the average is for all previous Tuesdays, for all previous Wednesdays, for all previous Thursdays, for the past week. And we're also going to calculate how much the previous week had varied from the average. So if we know that on Tuesday the average is 10, but on last Tuesday the actual score we saw, the number of cases, or in our case the number of clicks, was 12, then the sickness is 0.2 for that day. And we're just going to average them all up and divide them. So we're going to get the average difference for each day to the previous days of the week. And we're going to take that and calculate our availability, which is simply for the current day of the week, how many clicks have we usually seen, and times that by the sickness. So over the last week, how much has traffic been moving up and down, and that gives us our estimate. We then plug the estimate into our Poisson calculation, and that spits out a probability, saying, given this estimate, what's the probability of having seen the number we actually did? And if that number is less than a certain sensitivity, less than our configurable parameter, we signal alarm. If it isn't, we carry on. And there's just a little bit more code that fills up the window. So all we're actually doing is sticking the day of week into an array and summing over it. So the interesting thing there is, the different thing there is the Poisson distribution. Now, the normal distribution was a smooth line, but this isn't. It's a bar chart, because the Poisson distribution only deals with integers. It's about events. It's about counts of things happening. So this is a Poisson distribution for 4, I think. And if we get 4, if our estimated value is 4, the chance of seeing 5, pretty high. Like, we shouldn't be surprised about that at all if we see a 5. We should be just as confident of seeing a 4 if our average is that. And it falls off as we move away. And this models the behavior really, really well. So we find if we plot our estimate against it using this algorithm, we track the data pretty well. Not perfectly. We actually get a false alarm, but we only get one day to detect. We kind of get the best of both averages because we've included this extra aspect of data. We've included this extra average, which we are tracking. And doing larger anomaly detection, you will track more and more averages. You will pull more and more numbers together and look for correlated differences in them. You will look for when all the measures go up at once. This is good for clicks, and you can use the same thing for a lot of different kind of measures, like we were saying with the phone measures, the average top-up, the average call duration, the average number of calls per day. Anything like that can be tracked in a similar measure and can be detected based on previous activity. But of course, a lot of fraud doesn't happen around clicks and ongoing activity. It happens around transactions. And how would we detect those? Because a lot of the time, a transaction is the only interaction you've had with a site. You go onto the site, you purchase a product, you go away. That's entirely legitimate, and there's no history to compare it to. You need a kind of different way of approaching it. Well, we can take advantage of the fact that fraud commonly causes patterns, and we can encode looking for those patterns into our systems to attempt to detect them. So this is where rules and signatures come in. This is where you start describing how fraud looks and let your system tell you whether you're getting it. Every domain is different. For example, for people in the kind of auction space, it used to be at least that if you were going to create a fraudulent, do an auction fraud, then you needed to have a lot of reputation on the site. You needed to have a lot of whatever karma measure was used on the auction site. So there would be a pretty common pattern. Fraudsters didn't want to hang around for a long time, so they would buy a lot of low-value items from sellers with high ratings over a short time, so they could build up their feedback. And they would go out and they would maybe do some high-value transactions, so they look trustworthy, but with other fraudulent accounts. So a fraudster wouldn't just do one account, they would do a whole bunch of accounts and have those do some deals. So they're paying the auction fees, but that's their only cost. And if they can make enough on the back end of making the fraudulent transaction, then it's worth it for them. And you can encode knowledge about that pattern into a set of rules and flag up accounts, flag things for people to look at. So though it is very industry specific, I thought I'd just talk about some of the kind of indicators you might want to consider in a generic e-commerce sense. So one of them, like we said, is this the first time the customer's made a purchase? Just that on its own should give you a question. Just that on its own should be considered. If they have made a purchase before, how similar is this purchase to the previous one? If you've got someone that buys a book every couple of months and suddenly has bought 11 flat-screen TVs, something suspicious has happened. How is it being shipped? Just like we don't tend to deal with everything. You know, we have a big problem with some UX, we get in a UX consultant. People committing fraud do the same thing. They won't all do the end-to-end of the operation. A different group of people will steal the credit card numbers. A different group will make the orders. A third group will receive it. It's separate people, and so they want to get that bit done as fast as possible. Receiving stuff is one of the riskiest parts. So they will ignore free shipping. People will just pay. They don't care. It's not their credit card. They can just pay a bunch extra to have the stuff shipped there immediately. They might ship to locations that are not usual. If you ship mostly to homes and suddenly you're shipping to an industrial location or you're shipping to a cafe, that's suspicious. Something is going on there. And are there lots of orders going to the same address from many cards, or vice versa, one card to many different addresses? That can be indicative of something unusual. Not necessarily a red flag in itself, but something that can be part of a combination. You can go to all sorts of levels. One interesting thing I saw was comparing the name on the card to the email address used. Lots of people don't have email addresses that match up, but lots of people do. And it's something most fraudsters aren't going to spend the time to go down. They're going to just use whatever email they have. Maybe a free email, or maybe even one of those disposable domains that just lets you access the email. You don't even have to create an account. So comparing the name, which we're doing here with similar text, and is going to just give us a score of how close the name is to the email address, whether it's close to the first part, close to the domain, is an interesting way. It can give you a positive sign or it can give you a negative sign. And in combination with the other rules, it could work well. What about the velocity? If someone, again, makes an order from you once a month, but suddenly has made 50 orders, or a certain card has made 100 orders in a very short time, especially across a network of sites, that's suspicious. This is what people like Visa and MasterCard can use to really pick up on this, because fraud is pretty easy to detect if you know all of the card transactions happening at a given time. You can see real correlated activity between a bunch of sites. And what about the speed of location? If someone places an order with you in London and then 30 seconds later in LA, something suspicious has happened. Look at geo-IP. If someone places an order with you and the shipping address is to Germany, the card location is the UK, and the geo-IP says they're in Russia, that might be worth looking at. Now, pros will use proxies. You can buy proxied computers from the same place that you're going to buy credit cards. So it's not a foolproof thing, but GeoIP can be a really good way of detecting how coherent an order is internally. And of course, what kind of thing is being ordered? If someone is ordering, well, ebooks, they're unlikely to be committing a fraud. You can't really resell those. But if they're taking TVs or small electricals or iPods, iPads, that kind of thing, you can resell those. You can get good value off them. Anything that would do well on an auction site, you can get expensive handbags, jewelry, that kind of thing. Anything that could be resold for good money is much more likely to be targeted than this. But people are clever. In the same way as using the premium rate phone lines, they might use an affiliate network. So if suddenly one of your affiliates is doing a crazy amount of traffic to unusual places, that could be something suspicious. That could be something to look into. So this is cool, and we can write things like this, and we can compute a suspicion score. We can compute a score that we say, this is indicative of fraud. This is something to be investigated. But we're not learning from that. Anyone that has data already will have some fraud in their system that they've detected and stopped. It would be good to use that data, or data that is picked up once you have a suspicion scoring, and build something that looks for a more subtle relation, that combines the data you have with the rules, with the signatures you've detected. And that's what you can do using machine learning algorithms. Now, the one we're going to look at is the one Rasmus introduced this morning, support vector machines. And support vector machines are a fantastic, fantastic algorithm. It's a very simple to understand algorithm. It's very simple to use. The maths is insanely complex, and it works very well. So what we'll do is take all of our rules and encode them into a record. So rather than putting in a record like the price, the address, the order time, stuff like that, stuff that you would have in a normal transaction system, we will encode our rules into them. We will say, okay, what's the GeoIP country? We'll put that in. We'll put in whether the delivery address matches the card address. We'll put in a load of stuff here. You wouldn't want this in your transaction database as is. You wouldn't want this to be the only record you stored, but this is encoding the knowledge from our rules into a row. And we take that, and we would then use that information to classify against. So as Rasmus said earlier, what you do when you are using support vector machines is to try and find a separator between data in a certain dimensionality space. This is a two-dimensional space. It's just a graph. Each of the record entries, each of the columns in our row would have been another dimension. So we're really talking about, say, 20-dimensional space, and in reality, you're probably talking 100, 1,000 dimensional space, maybe higher, maybe less, maybe not all of them filled in, and SVM is great for those kind of situations. But the idea is the same. We have this space, and what we're assuming is that there is a way of drawing a line, or a plane, or a hyperplane, through all of those points, so that on one side, we have the fraudulent stuff, and on the other side, we have the legitimate stuff. But the question is, what line do we draw? We can draw that line, that works. But we could draw this line as well. Why is the other one better? They both separate the data, they both work. Well, one of the key intuitions at the heart of SVM is that the one with the most margin is the best, because that has the biggest possibility of error. You can be wrong the most with this one and still get the right answer. So what it looks for is to find the separating plane that has the largest margin to the points on either side. And one of the things that makes SVM fast is that it only needs to store the points that define the line. It can throw away all the others. So even if you have 10 million transactions which you're throwing into it, it might store 200, because those are the ones that define where the line goes through the data set. And that makes it very quick to use. Training might take a little while, but the actual use of it, the classifying, is done very quickly. And it's these that give it its names. Instead of points, they're referred to as vectors. And because they support the line, these are the support vectors the support vector machine finds. So we have to do something to actually see whether our classifier is helping, though. When we were looking at our anomaly detection, we knew we had days to detect and the false alarms. And we have a similar measure with our classifier, but we have to train it slightly differently. We have to take our data, some of which is fraud, some of which is legitimate, and give it to a learner that will give us a model. It will give us the support vectors. But we don't want to give it all the data because we need to know how it does. We need to know how it'll work on data it has never seen before. So we hold some back. We take a few fraud examples, we take a bunch of legitimate examples, and we don't give them to it on the training. And once we have the model, we take the test data and the model, give it to the classifier, and it tells us how accurate it is. So the way we would integrate this into a payment system is pretty straightforward. You just have your regular transaction processor, and as well as doing whatever it normally does, it would ping off to a classifier, which would just say, hey, this is fraud, or this is not fraud. And you would take whatever action you needed to take. We'll talk more about that in a little bit. But then you would have your transaction database be the source for your learner, so that as you got more examples of legitimate and illegitimate traffic, you could pass them to the learner and your detector would get better. So as you got more fraud or more legitimate traffic, you could improve the quality of your detector. But it's important to note that it's not this judgment here. This is a dotted line, because it's not automatically just chucking everything it said is fraud or not fraud into the learner. It's only doing ones that have been manually verified, because otherwise it's kind of listening to itself. It gets into a loop. So the code we're using is libsvm. That's available in package management most places. It works on Windows as well. It's pretty widely available. And there's a PECL extension, which you can just install via PECL. There's also Windows builds on this, which I can give you the URL for if you're interested later. And what we will do to use it is pretty straightforward. We need to take the data we had earlier and transform it into the format that libsvm uses. libsvm views everything as a range, a float, from range -1 to 1. So we have to transform everything into that. If it's a Boolean, like, hey, is this order coming from China? Well, we will just say 1 or -1, true or false. For the price, we'll take the average. So we'll go, if the price we have ranges from 50 quid for an item to 200 quid for an item, we'll have 50 quid be represented by -1 and 200 quid be represented by 1 and work with that same basis so that we transform all the data in the same way. We take all of our rows like that, and then we pass them to our train function. And because fraud is rarer than non-fraud, we can actually weight it and say, yeah, we actually think this category is more important. Because by default, it's going to not quite get it right. It's going to assume the two classes are even. For example, if you're doing spam detecting, actually the amount of spam and legitimate is pretty close. For some people, it's way more spam than legitimate, but for most, there's a lot of spam and there's a lot of regular email, so 50-50 is okay. But for fraud is way rarer, so we want to be able to tune that. And in fact, there's a lot of other parameters we can tune, which you can read about in the documentation. And what that does is gives us a model. The model allows us to make a prediction. So we then are just looping back over the test data and making a prediction about that. So this is just checking, we gave you this data to learn on, now is it correct? And that allows us to make sure we haven't ballsed anything up. We haven't sat there and thrown some invalid data into it and got an awful thing. So what we can do next is actually take our test data. So this is data we've never seen before. It's coming from a new file, and we pass that with our new model that we trained before and make the same predictions. And for each one, we're just going to calculate these 4 values. True positives, so that's where it said it wasn't fraud, and it wasn't fraud. True negatives, where it said it was fraud, and it was fraud. False positive, when it said it wasn't fraud, but it was. And false negative, when it said it was fraud, but it wasn't. And overall, we just calculate the accuracy, which is the 2 true ones over the lot. So what percentage of the time we were correct. And the values we get are pretty good. Without doing anything, without doing any optimization, we can get a 0.9998 accuracy on the training data, which means we couldn't quite separate the training data perfectly, which is accurate. In real life, you rarely can separate things perfectly. It's an indication you need to go back and change what kind of data you're giving to the algorithm. And we find on the test data, which we'd never seen before, we get a good accuracy as well. So we can do this. We can build something that can do this. And your accuracies may vary from this, depending on what your data is, of course. But how would we then integrate it? Because as much as this is important, as much as this is great stuff to work on, it's almost more important to do the other stuff. Because this bit is automated. You detect some fraud, and you know it's there. But what happens next? Someone has to look at that. And building the tools to do that can be almost more important. If you look at the stuff PayPal has built for fraud detection, a great deal of it is for analysis. It's not for just detection. It's actually for looking at the data and finding out where the fraud is happening, who is doing it, and getting as much information as possible so they can stop it from happening, so they can validate whether it has happened. And then you have to update the system. So like I said, you don't want to have the classifier listen to itself. You want to have the classifier get new data, new information, and that has to come from the information it's suggested being validated. So if it flags something as fraud and it's not, that can go back. If it flags something not as fraud, it doesn't catch it, and you later determine it is, that's really important to go back into the training set to make your detector better. But it doesn't just listen to itself. So there's a tool there that is usable, but we don't always want to work with PHP for these kind of things. We might have other demands. There are some great libraries out there, the wrap-libsvn and other tools. You've got Shogun in C++, Weka, which is kind of unpleasant, but in Java. And one of the most interesting is Mahout. And Mahout is a Java system that is built on top of Hadoop. So it's really designed to do this learning at very large scale over very large data sets, which not everyone has, but if you do, it might be an interesting tool. I mentioned that GeoIP is important, and I also mentioned that Visa have ways of detecting things because they see so much fraud happening across their network. Well, Quover and MaxMind are two of the big GeoIP services, and they actually do offer fraud products which give you some of that network effect, that give you some of that benefit to tap into, so they're interesting. And sorry about that. The other thing that they can do is allow you some degree of access to what everyone else is doing. So you can see on their network, there have been issues around this, there have been issues around that can give you some good information to work with. And of course, do the basics. Verify by Visa, secure code, they're not great systems, there are ways around them, and they are, in many ways, just a liability shift. But they do reduce fraud slightly. And doing things like CVV verification, doing things like AVS verification, all that kind of stuff reduces fraud from that 0.2% to that 0.1%. It makes it rarer. So it's important to do the basics, and it's important to be able to make your system the house with the alarm, so that the fraudsters go down the block so they look somewhere else. So I hope I've given you a little bit of an idea about some of the ways people use to detect fraud, and maybe some ideas to go and look for and have discussions about in your own businesses, and that's about it. Thank you very much. How are we on? Do we have time for questions?
We have 5 minutes for questions.
Lovely. Mark?
So just a question about SVM. So
Yeah.
If you give it, say, there's 100 properties you think might be important, but actually most of them are rubbish,
Yeah.
can SVM tell you, no, 80 of those are completely useless, don't bother me with those?
It's not like it's going to flag up to you and say, these are bad values. I mean, it's important to actually test some of this stuff. So where we had a test set and a training set, you would, in reality, usually have 3 sets. You usually have a test set, a training set, and a validation set. And what you would do is bounce between 2 of them, trying out different variations to maximize, and then finally test that on the test set so you have something truly clean. And what you do at higher complexity is actually divide your data into a whole bunch of things, and then for each situation, train on, say, a quarter of the data, test on another quarter, validate on another quarter, and mix it up so that you're constantly looping through the whole training and testing process with different sets of data. SVM really doesn't care about the level of data you have or the sparseness of data. It's good at dealing with very big matrices that are mostly nothing. So you can usually be a bit excessive and chuck a bit more data into it. And the problem is more generally that you don't have the right data than you do. But yeah, it's completely possible to get into that situation where you've chucked a lot of stuff of it, most of which is doing nothing.
Does it worry you that fraudsters might use this software to design better frauds?
Yeah, of course. That's what I would do. You constantly need to be. If everyone here started using like really good GeoIP detection to pick up fraud, one, you probably pick up a lot of fraud right now, but then in 6 months you won't. People change how they're working constantly, and this is one of the things that makes it difficult. the software itself is unlikely to change, but the kind of data you're putting into it is. So as different techniques evolve, different signatures appear, and different opportunities arise, you're going to see more of that kind of fraud. So, for example, chip and pin has had a big effect on how fraud is done with cards in the UK. It doesn't mean that there's less fraud per se. It means that it's moved to different areas. So it is a constantly evolving thing. Yeah. Oh.
Hi there. You mentioned the accuracy score right on one of your last slides. The score that you're using has the same problem as the original kind of little grid you showed before, where your accuracy it's not a true measure of exactly how accurate you're recording the data. No. Would it not be better to use something like the F1 score?
Yeah, F measure. I mean, that's a good point. So Neil was making the point that accuracy is kind of a bad measure because if I just took a fraud that is only 1 in 1,000 cases and I say it's not fraud all the time, like literally I don't make a detector and just say it's not fraud, my accuracy would be really good because it's so rare. So yeah, there are scores like the F measure and other statistics you can compute that account for unbalanced classes a lot better. Absolutely right. You would want to use those, and they're in almost any introductory machine learning text. You should be able to find some information about that, or grab me afterwards if you're interested. But yeah, great point.
I think we've got time for just one more.
I've got one.
Oh, Marcus has one. I feel bad.
I just wanted to ask, how did you learn this stuff? Is there some literature that you recommend that targeted towards software engineers?
Some of it came out of, there's a good book it came out actually of information retrieval. I was quite interested in that, and there's a good book by Chris Manning, which talks about machine learning actually as part of information retrieval, so I kind of got interested in it then. And Stanford, yeah. Now, this month. So one of the free Stanford courses is the machine learning course, which is excellent. Very, very good. It uses Octave, which is kind of like MATLAB for most of the programming, but you will get all of the concepts very well explained. It's all done online, so I definitely recommend that. Yeah, excellent course. And there are a lot of resources out there. Machine learning people like to talk, so there's plenty of papers, plenty of information online.
Okay, so an absolutely last question, Marcus.
You couldn't get the graph up where it's cutting the dividing line up, could you?
Yeah, probably. One of these.
Yeah, that'll do it. That one's perfect. If you've got noisy data, if one of those little crosses is on the wrong side, that's going to screw this thing up royally, isn't it? What's the best way you've found of coping with it?
Well, there's two things. For one, you are almost always not going to be using an actual straight line. So by default with SVM, it uses a Gaussian kernel. So it actually is mapping it to more spaces, which means it can cope with it. But if you actually just have bad data, there is a parameter in SVM called C, which is how much it will trade off having a nicer, simpler solution for having things on the wrong side of the line. So it'll prefer a simpler curve with some erroneous data if you give it a certain value of C. And that's what I would generally do, because you don't know this is happening. So you're just seeing it when you're doing validation. As you look at the test and training data, you're seeing you're not getting the results you're expecting, and you can vary some of those parameters and see how it goes. And actually, there are some tools that will automatically test a whole range of parameters and give you information back.
If you found that to be enough, because
depends on the data set. It is very, very varied whether you can get good information out of it, but I found if I have a problem with that, I don't worry about the algorithm, I go back to the original data.
So thank you very much. That was a really interesting talk.